Hey guys, welcome to another video on differential equations. So today's going to be about orthogonal trajectory. What does that mean? Orthogonal trajectory will just mean you'll have two functions and they will intersect and have an orthogonal intersection. So basically, we'll have an m1 that will equal a negative 1 over m2, and this m1 is going to be related to a function of xy, which will be dy dx. And our m2 will equal negative 1 over f of xy, which will also equal dy dx. So the point of doing all these problems will be to use this idea. We want to find m2 from our m1. And you'll notice that we're going to be using that all throughout. So for this problem, we want to find the orthogonal trajectory of this given family of this function. I'm sorry, not this function, this equation. And C1 is just our function. So we're going to be following a few steps here. I'll go ahead and make a list of steps that we want to follow to solve this equation. So first we're going to isolate our C constant. Secondly, we want to find our m1, which again, that was equal to dy dx. And third, we want to find our m2, which is equal to the negative 1 over m1. So it's just going to be the negative reciprocal. Once you find your m1, you just take your negative reciprocal and you have your m2. So we'll go ahead and follow those steps. Alright, so let's get started. So, first, you'll have these two functions, and we want to see where they'll intersect. Like I said, this was orthogonal trajectory, so these two equations will at some point create a 90-degree angle with the tangent line. So what we're going to do is we're going to move this negative 4 to the other side. And then we're going to divide by 2y. We're going to get dy dx equal to negative 2x over y. And remember, our m1 was equal to dy dx. So this will equal m1. Well, we said that to find m2, we just take our negative reciprocal of this. So I'm going to go ahead and put that equals to y. That negative will drop out and it'll become a positive because we're taking the negative reciprocal. And like we said, this was also equal to dy dx. So we're going to go ahead and solve this. Now, how do we solve this? Think back to separable differential equations. So we're going to solve that using our separable differential equation technique. So we'll go ahead and put all the y's on one side and all the x's on one side. And that's going to give us dy over y is equal to dx over 2x. And if we integrate these, both sides, we'll get the natural log of y equal to 1/2 natural log of x plus the natural log of c. And why do you natural log the c, if that's your question? Well, we don't know what this constant is at all. It could be anything we want it to be. So I'm going to go ahead and put this here. And I'll write it one more time. Take the x to the 1/2 will become the square root of x which makes it easier to take the inverse natural log of all the terms, and you'll simply be left with y is equal to the natural log of the square root of x plus c, and you know what I should have done is I should have combined these two terms using log rules. So before I those two terms, actually before I any terms, I will combine these two terms using natural log. If I am adding natural logs, I will multiply. Right? So I can now apply my inverse natural log, and I'll get y is equal to the square root of x times c. And that will be my answer. And to point out, what does this answer mean? Well, this means that this equation will be perpendicular. This equation will be perpendicular to our first constraint, which was 2x squared plus y squared equal to c1 squared. That's what this answer means. So we'll go ahead and do another problem where we'll have this equation. And our goal is to make this equation perpendicular to that equation. So let's go ahead and do that. Remember, our first step was to isolate the c. So this part may be simple. Isolating that c1 will equal 1 over y minus x. Okay. Now how do we find our dy dx? Well, what we'll have to do is implicit differentiation. If I spelled that incorrectly, I'm so sorry. Well, we'll implicitly differentiate that, and we'll end up with 0 is equal to negative 1 over y squared multiplied by y prime minus 1. And we'll go ahead and add this term to this side. And that y prime follows it. Okay, so now we'll have 1 over y squared times y prime is equal to negative 1. We'll go ahead and multiply this y squared to both sides. And we'll end up with y prime equal to negative y squared. By definition, our y prime is simply dy dx, of course. That's going to be equal to negative y squared. So, like we said, our m1 was equal to dy dx. So, we're looking for m2. So, m2 will be the inverse reciprocal of, the negative reciprocal of our m1. So that'll just become a positive 1 over y squared. And like we said, m2 was also equal to dy dx. And we'll go ahead and do our separable differential equation technique. We'll get the y's on one side and the dx's on the other. So we'll have y squared dy equal to just a dx. And we will take an integral of both sides, and we'll end up with 1/3 y cubed equal to x plus c. And again, what does this answer mean? Well, now this equation is perpendicular or orthogonally. It's orthogonal to our original equation, which is y is equal to 1 over c1 plus x. So this is orthogonal to this. Let's try another problem. What if they didn't give you another equation to see if you're orthogonal to it? What if they just gave you this? Now, it probably does look pretty ugly because we have those functions within each other. but that's okay. What we first want to do is solve for our c and isolate it. And then our m1, and then our m2. And our fourth step, which I didn't mention because I just wanted to show you, is that it becomes a separable equation, and we just integrate. So I will start off with eating both sides, and we get e to the y power equal to tangent x plus c1. I want to solve for the c1, and I'll subtract tangent x to both sides. I'll get c1 is equal to e to the y minus tangent x. Okay, so we solved for c1. Now our next step was to find m1, which is dy dx. So how do we find dy dx from this equation? Well, again, we'll also implicitly differentiate. And the derivative of the constant is 0. The derivative of e to the y would be e to the y times y prime minus the derivative of tangent x secant x squared. Secant squared x, sorry. Now we want to isolate our y prime, which will be our dy dx. So we'll just solve for that. And then we'll divide our e to the y. That will be gone. Well, it's not gone. It just reduces to 1. Okay. Well, that's dy dx equal to secant squared x over e to the y, which we said was our m1. And we want to find our m2, which our m2 was the negative reciprocal. So that will just become m2 will equal negative 1 over secant squared x divided by our e to the y. That would go up. That'll equal negative e to the y over secant squared x. And again, that is equal to dy dx. So our fourth step said that it was going to become a separable equation, and we'll integrate. So we'll go ahead and integrate that. We had dy dx equals to the negative e to the y over secant squared x. So we'll integrate both sides, and we'll get negative e to the y dy is equal to negative so if, let's say you didn't want to deal with that secant squared x, let's think back to trig. Secant squared x is just going to be, this is 1 over secant squared x. So that's going to be equal to cosine squared x. Right? Okay, so we'll get cosine squared x dx. How do you integrate cosine squared x dx. Well, we'll have to apply this power reduction. Cosine squared x will be equal to 1 plus cosine 2x divided by 2. So we'll go ahead and plug that in. 1 plus cosine squared x over 2 dx. Alright, so the integral of negative ey with respect to y will simply be negative e to the y equal to, this integral is negative 1/2 quantity x plus 1/2 sine 2x plus c. And we can go ahead and divide our negative 1 from our e to the y to all the terms. So this will become e to the y equal to, that becomes positive, 1/2 quantity x plus 1/2 sine 2x. And this negative will be absorbed, quote unquote, into this c constant. So you could still call it c, or you could call it c2. I'm sorry, I lost this negative. Did I lose a negative? No, I did not. Yeah, so this will be your answer. I thought I was supposed to have a negative here, but I did not. And that's how you solve the orthogonal trajectory differential equations. And these would be just applications of first order differential equations. Thanks for watching. Hope this helped.